Okay, so welcome to the 37th video in the Discrete Structure series, and this is going to be the last video in the topic of recursion. So we have finished looking at recursive definitions, structural induction, and also recursive algorithms. So today we'll be closing the chapter with a discussion of a small topic, and this one is proving recursive algorithms correct. So this task of proving recursive algorithms correct makes use of mathematical induction and often the strong mathematical induction. So we'll look into two algorithms that we previously did under the topic of recursive algorithms. And in here, we'll try to prove that those algorithms are correct. But before that, I want to have a quick discussion on why the process of mathematical induction is used to prove the correctness of recursive algorithms. So we know this for multiple lectures that any recursive definition has two aspects. One is going to be the base case and another is going to be the recursive definition or the recursive step. So the task of proving a recursive algorithm correct requires us to show that no matter how many times we apply the recursive step, the result obtained is still valid. So let's say I write a recursive definition for 2 raised to the power n. We know that we do this by using a base case. f0 equals 2 raised to the power 0 equals to 1. And fn would just be the previous n times 2. And in this context, what does it mean to show that this algorithm is correct? It simply means that if I take this base case and keep applying this recursive definition any number of times, the result is always going to stay the corresponding power of n. And that is where the principle of induction comes into play. It is the same like saying if I apply this recursive definition one time, it should work. If I apply the recursive definition again, maybe 2 times, it should work. If I apply it 3 times, it should work, and so on. For any number of times that I choose, the definition should work. And this idea of proving something for any number of times is the core idea of mathematical induction. So the problem of proving this recursive algorithm correct is same as the problem in mathematical induction that says prove that the recursive definition is valid for any number of times it is applied. And proving that a definition is valid for all possible number of times that it can be applied is equivalent to proving that the algorithm always works. So the process of proving a recursive algorithm follows directly from mathematical induction, but as suggested here, it might sometimes require the property of a strong induction. But we know that the philosophy is more or less the same. In normal mathematical induction, we are allowed to assume that a proposition is true for k. And using that assumption, I needed to prove that it was also true for k plus 1. And to prove a recursive algorithm using mathematical induction, I'll do exactly the same thing. I'll assume that the recursive algorithm works when the definition is applied k times. So what we get upon applying the recursive definition k times depends on the definition itself. In this case, if I apply the definition k times, I'm simply going to get 2 raised to the power k. But we have studied more complicated structures. If I use the recursive definition of a tree and apply that definition k times, I'm not going to get any number. I'm going to get some arbitrary tree. If I apply the recursive definition of a well-formed formula k times, I'm going to get some random well-formed formula. So what exactly to assume when you are assuming k depends on the problem. But the idea is you need to prove k plus 1. If a recursive definition is applied now one more time, the definition should still hold or it should still be valid. And we have already discussed about strong induction in the past. In strong induction, I'm not forced just to use k, but I can use everything from 1 to k. That means it is not just the definition applied on the kth step that I can use in order to prove k plus 1, but I can use all definitions from the base case up to the kth step. And using all of that, if I can prove that applying the definition one more time does not violate the definition, my proof by induction will be complete. So I'll say a couple of things. First thing, you need to be familiar with mathematical induction and strong mathematical induction. We have complete videos and solved problems in that topic. And we are going to apply the concepts in strong mathematical induction in order to prove correctness of certain algorithms in today's video. And assuming that you have some idea, I'll tell you the second point. The type of problem that we'll solve today involves an algorithm. So we will be given an algorithm and we'll simply be asked to prove correctness of that algorithm. So the first thing that we'll need to do is to look into each recursive algorithm and detect if a result at a given step is only depending on the previous step. If the recursive definition only makes use of the previous step, for example, n is defined in terms of n minus 1, the previous step. So that means we can just use normal mathematical induction because just the previous step was enough to prove the next step. But if we see a recursive definition where just the previous step is not enough, we need to use strong mathematical induction. Because if we consider a formula for a Fibonacci sequence, nth term would be the sum of n minus 1th and n minus 2th term, okay? So because this recursive definition is defined this way, in order to derive Tn or to prove that Tn is true, just using Tn minus 1 is not enough. So proving these kind of algorithms correct will involve a strong induction, because I need to depend on previous two terms in this case. So one last time before diving into the problems, in case we need to use strong induction, we are allowed to use the base case and every case until my assumed k. And I'm allowed to use any of those facts in order to derive k plus 1. Alright, so next we'll look at a couple of algorithms and prove that they are correct. So I'll put a question here. Prove that the following algorithm for computing a raised to the power n, where a is a non-zero number and n is a non-negative integer, is correct. And the algorithm is given. I'll just put it here quickly. This is an algorithm that we already looked at. Okay, so this algorithm is given to me. Procedure power, and we know the base case. If the power is 0, we return 1. A power 0 is 1. Otherwise, we just return the product of a and the power of a raised to the power n minus 1. One lower power. And this power function will invoke itself until the power breaks down into the base case. And once the base case function returns, each subsequent return will multiply by a. And ultimately, I'll get a raised to the power n as my final output. Alright, so based on our earlier discussion, let's first decide which type of proof method we'll use. Do we use strong mathematical induction or the normal mathematical induction? So for that, we look into the recursive definition like we talked about. In this case, the recursive definition is returning a times the power of a and n minus 1. Therefore, the definition for n is only depending on n minus 1. Just the previous step is enough to prove the next step. So that means I can just use the normal mathematical induction. K implies k plus 1, which is the same as saying I need to prove n minus 1 implies n. Okay, but what to do if asked formally? So I'll start from here, the actual solution. So we are giving a mathematical induction proof. And the thing that I need to prove using induction is that the function power correctly calculates power. So power of a and n should properly return a raised to the power n. So this is my statement, or this is what I need to prove. The first step in induction is deriving the base case. So the base case comes when the exponent n is 0. So when I plug the exponent at 0, I just get a raised to the power 0, and that is equal to 1. And for the base case to be true, I want this function to successfully return that 1 whenever n is 0. Is that function doing that? It is doing that in this line. So in the base case, we'll say when n is equals to 0, the function power a comma n returns 1. You can refer to the line. I'll say it returns 1 from line number 2. Also, I can verify that by using the value that I want, a raised to the power 0 is equals to 1. Therefore, I can say the function works in the base case. So just following exactly the process of induction, but according to the function or algorithm that is given to me. But this one is pretty basic, but the same process will be used to analyze more complicated functions. Alright, so the next thing that we do is to assume that pk is true. So let me make my inductive premise. I'm assuming that if the power is any random value k, the function is returning the correct result. So I'm essentially assuming that if I plug the values a and then k to my power function, this successfully returns a raised to the power k. And this is my inductive hypothesis. Now in my actual induction proof, I need to prove that if the recursive definition is applied one more time, it still works. That means if I take the power of k plus 1, it's just going to be a raised to the power k plus 1. So using this fact, I need to prove this fact. So it is easy to show that. So we'll see what happens when we plug a and k plus 1 into my power function. It cannot hit this base case because now n is not equal to 0. Therefore, it will have to use the else statement in order to return this value. So I'll mention exactly that. Since k plus 1 is not equal to 0, function will return from line number 3. And based on this observation, I can say that the function is returning this value. Power, when I plug a and k plus 1, I see that the function will return in this pattern. So it will return a, and then the power of the same a, and then the n will get reduced by 1. And therefore, in this case, when the else is returning, it will just return a into power. And we see that the first argument is still a, and the second argument is going to be 1 less than the input. So I'm passing in a k plus 1 here. I'll get a k here. Okay. And does our hypothesis help now? We have assumed that power a of k is equal to a raised to the power k. So I can replace this whole power by a raised to the power k. And this will just be equal to a raised to the power k plus 1. A times a raised to the power k. So this proof will exactly be similar to the proof of induction. But you need to be able to look into the algorithm and figure out what it is returning in which case. So let us look at one more problem. So we'll prove the correctness of the recursive modular exponential algorithm that we looked at in yesterday's video. So I'm going to write the algorithm quickly. Alright, so we have already looked into this problem with a lot of detail under recursive modular exponentiation. And here our goal is simply to prove the correctness of this algorithm. But let me repeat the basics of this algorithm. This is an algorithm used to calculate b raised to the power n mod m. And this process is called modular exponentiation. And let me recall a few things from the previous lectures. The base case for this algorithm is b power 0 mod m. And we know that this is equal to 1 because b raised to the power 0 is just 1 and 1 mod m is just 1. And the idea of this algorithm was to start at a larger value of n, but each time it would look if n is even and n is odd. Depending on whether it was even or odd, it would return separate things. But no matter what it returned, this one or this one, we see that the size of n is reduced. So originally we have n in the input. Here we are calling with n by 2 and here we are calling with the floor of n by 2. So that means that the value of n will eventually grow smaller and smaller and eventually it will hit 0 and be the base case. So please go back and look into the algorithm if you need to. But for now, I'm moving on to correctness. I need to be able to prove that this function m power is correct. And that means that I need to prove that the m power of b, n and m correctly calculates the value. It is equal to b raised to the power n mod m. And now we know the pattern. Let's try to evaluate the type of induction first. Here we can say that n is not simply depending on n minus 1. So that means just the previous value is not enough to prove the last value. Because you see b raised to the power 10 is not defined in terms of b raised to the power 9. It is defined in terms of b raised to the power 10 by 2, which is 5. And because n minus 1 is not enough to derive n, the normal mathematical induction will not be enough and we'll need to use the process of strong induction. Alright, so let's get started with the base case. So in the base case, we need to check if the function is returning correctly when n is equal to 0. So the base case is for n is equals to 0. And we know that m power b, and when I pass n as 0, this is 0, and m returns 1. And I can say it does that from line number 3. And also if I check this side, if I take b power 0 mod m is equals to 1 mod m is just equal to 1. So whatever the function is returning and whatever should be returned is the same. So we'll say that the base case holds. Now we'll form our inductive hypothesis or the inductive premise. And here we discussed that strong induction would be needed because an input n is not simply depending on n minus 1. It is depending on n by 2. And I want you to remember what we did in strong induction. We assumed everything from 1 to k and used that to prove k plus 1. So what this simply means that in order to prove the next step, you are allowed to use the previous step and all other steps before it. But in the case of my problem, working with k is much easier than k plus 1. So I'm going to rewrite this equation as follows. So I'm going to say that I should assume everything from 1 to k minus 1 and then use that to prove k. Okay, saying this and saying this is exactly the same. So this means that I can assume that the algorithm is correct for all possible powers n from 1 to k minus 1. So we are assuming a j so that when the j is between 1 and k, it could be 1, it could be k minus 1, it could not be k. So I'll write it as follows: 1 less than j less than k. Okay, cannot be equal to k, should be less than k, but can be equal to 1. And when j is in any of this range, I want to assume that the procedure works correctly. Okay, so you might be tempted that our assumption might contain these recursions, but no, I'm just looking to see that the function works correctly and returns the value of b raised to the power n mod m like it should. So for any j in this range, I'm simply assuming that the function m power when plugged with b, that exponent j and m works correctly. This returns b raised to the power j mod m. So let me tell you again, what we assume on the inductive premise depends on what we expect of the function, not what is defined in it. We want this function to calculate b power n mod m correctly. That's what we assume. It works for all inputs less than k. And using this hypothesis, we need to show that it correctly calculates the modular exponentiation for the next higher power. So the powers we consider here were from 1 all the way up to k and not including k. So the next higher power from this would just be k. So using these facts about all j's that are less than k, I want to prove that the function also works for k. So what I need to prove is that if I were to plug the m power with k this time, this should return the right result. So this should be equal to b raised to the power k mod m. So I need to prove this using this as an assumption. And where do these definitions come into play? They'll come into play during my proof, because in order to see what m power b k m is returning, I'll need to look into the function and see where it is doing what thing and returning what thing. Alright, I'll just clear up a little bit of space here. Alright, so let's get started without proof. So our objective is to show that the function works when this power is k, given that it works for all powers less than k. And you see, in this stage, I was simply assuming. I was assuming that the function worked correctly. So I just assumed that this should be equal to the correct result b power j mod m. But this is something that I need to prove. So I'll need to look into the function and see its behavior to see what it is returning. So what I want to evaluate is the value of m power of b, k and m. And this time k is not equal to 1. This is not the base case. Then we know from this function definition that if n is even, it returns this thing, and if n is odd, it returns something else. So we'll need to do the same thing here. We need to show that this works, that this is indeed equal to b raised to the power k mod m, regardless of k being even or odd. So we'll do that in 2 steps. We'll see if k is even, and we'll also see if k is odd. Alright, let me also move this assumption on top and clear this part of the board. So I'll start with this part. Whenever k is even, the function will return according to this statement. So it's going to return the m power with b n by 2 and m, square it, and then mod m. So this is what it is returning. As I can see here, I can mention like last time, it is returning this from line number whatever. And here my input is k, so this will just be k by 2 instead of n by 2. Now what do I do next? See, I can use my inductive hypothesis now. This value k by 2 is definitely between this range of 1 to k. It is less than k, it is greater than 1. Do you agree? For any k, it will happen. Therefore, the m power of b k m will be one of my base cases. So I have already assumed that for a number like k by 2 which falls in this range, this formula works correctly. So that means this should just be equal to b raised to the power k by 2 mod m. We should square it and then mod m. So all we did was replace m power b k by 2 m was b raised to the power k by 2 mod m, because the power k by 2 fell within my assumption, where I assumed the formula would work correctly. And this will just be equal to b raised to the power k mod m. So nothing fancy here, just a few laws of modular arithmetic. I'll show you the algebra of why this works maybe, but let's get on to the case for when it is odd. And I know in this case, it is returning using this statement. So I'll get started by writing exactly the same expression over here. Just replace the n with a k. But the idea is going to be the same. The m power will be replaced by b power k mod m from this rule. So let me write down what happens after that. So this m power b n by 2 m can simply be written as b raised to the power floor of n by 2 mod m. So just following the formula, we square this value mod m, multiply the whole thing with a b mod m again, and then the whole thing is taken mod m. And again, since I'm looking for k, this variable will just be k by 2. And let me write this down first. This will just be equal to b raised to the power 2 times the 4 of k by 2 plus 1 mod m. And this is also equal to b raised to the power k mod m. So I know there could be a couple of confusions. So let me start resolving them one at a time. So first thing, 2 times this plus 1 is just equal to k. And this only applies when k is odd. So let's quickly verify. When I have an odd number here, like let's say k is equals to 5. When I divide 5 by 2, I get 2.5. But I'm taking a floor of this value, right? So when I take a floor of this value, I only get 2. Now when I multiply this 2 with this 2, it becomes 4. And when you add 1, it becomes 5 again. And it only works when k is odd, because when we divide by 2, we lose a 1. Because this k is an odd number like 5, when I divide by 2, I go down to 2. But if we had an even number like 6, when we divided it by 2, it would give exactly 3. And when I multiply by 2 again, I go back to 6 without having to add any other 1. But when it is an odd number, when I divide and take the floor, I lose the extra 1. So that 1 is being added here. You could check with other numbers. Hope this transition is clear. Alright, let us next address this one. We talked about a property of modulus in our earlier video. If I have a, b mod m, I can take mod individually with a and b and it will not change the result. So this will just be equal to a mod m times b mod m and the whole thing mod m. Okay, so when I have a product of 2, 3, 4, any number of terms, I can reduce each of those terms mod m before taking the product. That's the basic idea. So let me show you how this is equal to this. So let me write an equals here. By the way, you can directly write this step from here. But if you want to see why this works, we are doing like this. We are saying b raised to the power k by 2 mod m. And you know, squared means being multiplied with itself, right? So I can just write times the same thing and I have a mod m outside. And you see how this is now equal to this rule over here. A times b mod m is equal to a mod m, b mod m, mod m. So I have something b raised to the power k by 2 mod m, b raised to the power k by 2 mod m, and mod m outside. So it's like jumping back from this step to this one. So I know this will just be equal to b raised to the power k by 2 times b raised to the power k by 2. And the whole thing mod m. And you can now see this is just equal to b raised to the power k by 2 plus k by 2 mod m. And this will be b raised to the power k mod m. So from this to this, we are just using this law of moduli. Now there could be one more confusion of why I can write this expression from this one. So let me give you a hint on this one as well. I have b raised to the power k by 2 mod m multiplied 2 times. It is on squared. So I have 2 times the floor of k by 2 over here. And then I also have a single b multiplied over here. This is b raised to the power 1. And that is giving my plus 1. So this one is also using the law of powers or indices combined with the law of modulus, just like we saw earlier. So I'll leave it for you to exactly derive these steps if you want. But I think the clear picture should be available, right? 2 of these things k by 2 and 1 of b. Applying the product rule of moduli. You can easily calculate this. And with that discussion, we have completed this chapter, the chapter of induction and recursion. We'll be starting our next video with a whole new chapter of counting and discrete probability. So that's all the discussion for today. I'll see you guys in the next one. Have a good day and bye.